In the previous video, we learned about centripetal motion and a specific type of centripetal motion called uniform circular motion. Now, centripetal motion occurs anytime there's a force that's perpendicular to the path of motion of an object. And that perpendicular force is going to cause an object to turn. That's centripetal motion, when an object changes direction as it moves. Uniform circular motion is a special type of centripetal motion that occurs when that perpendicular force is the only net force and it keeps changing direction, so it's always pointing toward the center of a circle. And honestly, that happens in the real world all the time, where we have objects that move in circular paths. Anything that's moving in a circular path must be experiencing a centripetal force causing uniform circular motion. We're going to extend our understanding of uniform circular motion today by taking a look at an example that occurs frequently in nature, universal gravitation, and specifically universal gravitation as a centripetal force. Now, this lesson is not just going to be about universal gravitation. We're going to learn about universal gravitation by comparing it to a few other examples of uniform circular motion as well. One more thing as we get started here. I want you to think back to when we were solving kinematics equations. Remember, there was a very methodical way we would go about solving problems with kinematics, where we would list out everything we knew in a table and the things we didn't know. We would identify the variable we were looking for according to what a problem was asking. And then as long as we knew all but 3 of the kinematics variables, we could use our 4 kinematics equations, and we'd have to pick the right one for what we were looking for, but we could use those kinematics equations to solve for our unknown values in that table. But it was a very specific way we solved those problems. The same was true of the force problems, where we had forces in the same line as motion. First of all, we would draw a free body diagram. Then we would use our free body diagram to write out our net force equation for the sum of all of the forces. Then our net force equation that was either ma or 0, according to Newton's second law. And then we would put those 2 net force equations together, and we would, figure out individual force values if we had to, or get something on a side by itself. There was a very methodical way of solving force problems too. We're going to see that with centripetal motion, uniform circular motion problems, there's not really necessarily one methodical way to do this. We're just going to borrow elements of the way we solve problems in the past. Yes, you're going to list the things that you know. Yes, you're still going to need to apply net force equations sometimes, because the centripetal force causing uniform circular motion is a net force. So you're still going to need to borrow from those techniques, but you're also going to see that we're going to be a lot more creative when we solve circular motion problems as we put things together. It's not always going to look a certain way. There's not just one way that these problems look. Fairly early on in this lesson, we're going to get to a practice problem, and then we're going to have some practice problems later on in this lesson. As we work those problems, I want you to pay attention to how we get a little creative with how we set up and solve these problems. And just pay attention to how there's not just one specific way of solving them, like it sort of was in the past. There was really one specific way of solving previous problems, but there was a much more formulaic way of doing it compared to how we do these types of problems. Okay, now let's do a little review. First of all, uniform circular motion results whenever we have a uniform centripetal force. What does that mean? Well, a uniform centripetal force is always perpendicular to the direction of motion. It's always the same size force, and it always points toward the center of a circle. And to maintain that last characteristic, pointing toward the center of a circle, that means that that centripetal force must be constantly changing directions so that it points toward the center of a circle. All right, we'll see that in some examples that we work, but that's one of the ways that we define uniform circular motion and centripetal motion. Centripetal forces are identifiable forces with identifiable agents. They are not forces in and of themselves. So when you're identifying the force, you wouldn't just say, oh, that must be centripetal force. You could say it's a centripetal force caused by friction, caused by normal force, caused by tension. You can identify the specific force that's causing it. And that's another characteristic of centripetal forces. They're not their own type of forces. We can always equate them to other forces that we've learned about in the past. Like in this practice problem, A small coin is placed on a flat horizontal turntable. The turntable is observed to make exactly 3 revolutions in 3.3 seconds. We have 4 questions here related to this. What is the speed of the coin as it rides to 5.2 centimeters from the center of the turntable? What is the acceleration at that distance? What is the force of friction acting on the coin if it has a mass of 1.7 grams at that distance? And then the last one, we're going to change the distance. What is the coefficient of static friction between the coin and the turntable if the coin slides off when more than 12 centimeters from the center of the turntable? All right, let's see how we would solve a problem like this. First of all, let me make a sketch of the problem. There's my radius. There's the speed of the coin. I'm going to call that VT, the tangential velocity, because I'm noting not just the speed, but the direction. And it's a tangential direction because it's a tangent to the circle at that point. Or in other words, it's perpendicular to the radius at that point. So it just barely skims the outside of the circle. So this is my basic sketch of what's happening in this problem. I'm also going to note that in order for it to keep moving this way in a circle, in order for it to just not fly off in the direction of that velocity vector, there must be a centripetal force that's keeping it moving in a circle. And that centripetal force must always point toward the center of the circle as this coin moves around on the turntable. All right, I'm going to need to do some math here to start solving this problem. And the first bit of math I'm going to do, I'm going to note that that tangential velocity can be calculated by taking the distance around the circle divided by the time it takes to go around the circle once. Distance around a circle is the perimeter circumference, 2 pi r. And the time it takes to go around once we noted with a special variable, capital T, for period. Do we know the period? Well, we know that it takes 3.3 seconds to complete 3 revolutions. And if that's true, we could just divide 3.3 seconds by 3 revolutions to get 1.1 seconds per revolution. Or we would just say the period is 1.1 seconds. We don't actually have to include the word revolution in there. 1.1 seconds is the period. Just because we know what period is. Period is the time it takes to make 1 revolution. So we just need to report the time value there. 1.1 seconds. All right, and then I could figure out the tangential velocity here by dividing 2 pi times the radius, 0.052 meters. I'm going to write this in meters per second. It says centimeters per second. Although in this case, centimeters per second would be just a fine value to report. I'm going to do meters per second. Reason for that is because I know later I'm being asked about force, and forces are in newtons, and newtons have kilograms, meters, and seconds involved. So everything has to be in kilograms, meters, and seconds eventually. I can calculate for number one, what is the speed of the coin? The tangential velocity, I'm going to be a little more specific than just saying speed, is 0.30 meters per second at 5.2 centimeters from the center. So notice I converted 5.2 centimeters to 0.052 without doing the extra math. You probably at this point just do that in your head, and I solved. All right, for number two, what is the acceleration of the coin? Well, the acceleration of the coin is going to be centripetal. It's pointing toward the center of the circle. Because it's moving around at a constant speed, the tangential velocity magnitude is staying the same, but that tangential velocity direction is changing. The only way anything can ever change direction is if it's accelerated because its velocity is changing. And a change in velocity is caused by acceleration. But we have to take into account this is centripetal acceleration, so we need to calculate it using our centripetal acceleration equations. Notice that I'm just treating this like centripetal acceleration. I'm not asking myself what force is causing this centripetal acceleration yet. Okay, so I can just use this regular centripetal acceleration formula, plug in what I know. I know the velocity is 0.30 meters per second. I just solved for that. I'm going to square that and divide by the radius again. And that's going to give me a centripetal acceleration 1.7 meters per second squared. All right, I've solved part two. Now what about part three? What is the force of friction acting on the coin if it has a mass of 1.7 grams? Okay, I'm being asked force, but I'm being given a value in grams. I have to be careful with that because force is kilogram meters per second squared. So I need to change grams to kilograms. And once again, I'm not going to write that conversion out. You could do it if you wanted to just double check and make sure you're doing it correctly. I'm just going to do that one, though, in my head. And I'm going to note, first of all, centripetal force, any kind of force, is mass times acceleration. Centripetal force is going to be mass times centripetal acceleration. So all I need to do is take my centripetal acceleration value, multiply by the mass. And that mass is 0.0017 kilograms. The decimal place moves over 3 places to the left to change to kilograms. And then times the acceleration I just calculated. It's just a straight up multiplication. I find that there's a centripetal force of 0.0029 newtons, causing this coin to move in a circle on the turntable. So if you were reading the questions as you've been following along, you may notice there was a part of number 2 we didn't answer. And that part of number 2 is also sort of a part of number 3 too. In number 2, it asks what is the magnitude and direction of the acceleration of the coin. And whatever that direction of acceleration is, that also has to be the direction of our force. What is the direction of acceleration? Well, because the only force is a centripetal force causing this object to move in a perfect circle, we know that both the acceleration and the force have to be directed toward the center of the circle. That's just a characteristic of centripetal acceleration, centripetal force, that we know that these forces need to be directed toward the center of the circle, and the resulting acceleration is also going to be toward the center of the circle, causing the object to move in a circular path. All right, now this last question is a little tougher. And here's the thing. These first 3 questions we could relate to one another because they all had the same radius and the same period. What are we going to be able to carry along to the last question? The last question asks, what is the coefficient of static friction between the coin and the turntable if the coin slides off the turntable when more than 12 centimeters from the center? So now our new radius we're going to be working this problem is 12 centimeters. Anything that used a radius of 5.2 centimeters is no longer valid. And you can see that in most of the work that I've done, I've plugged in 0.052 meters somewhere. So I got to get rid of all of that work. What about the period though? Is the period going to stay the same? Well, if you think about it, the way a turntable works is there's a rotating disc, and all points on that rotating disc are moving around the center in the same time. So we know that if a point near the center rotated around the center in 1.1 seconds to make one complete revolution, a point further out would also have to have taken the same 1.1 seconds. That's just how a rotating disc works, because all the points are fixed with respect to each other. Now, keep in mind, that's not true for all types of circular motion. If you have a bunch of moons orbiting a planet, for instance, all of those moons could have their own, it actually will have their own independent period. They're not all fixed to each other. They're not riding on a rotating disk. So therefore, the periods can be different. So I'm going to list 2 additional variables here. I'm going to list our period, and I'm going to list our tangential velocity from this part of the problem. We know our radius is going to be different because the problem says it. The problem says that in part 1, I have a radius of 5.2 centimeters. In part 4, I have a radius of 12 centimeters from the center. So obviously the radius is going to be different. What about the tangential velocity? Is that going to stay the same, or is it going to be different? Well, you can imagine that as you move further out from the center of the circle, you're going to be covering more circumference, a greater circumference, more distance over the same amount of time. So your tangential velocity is going to get greater and greater and greater as you move further and further away, as your radius becomes bigger. And then what about the period, 1.1 seconds? Well, we already established that that's going to stay the same. So I'm going to keep that period value here as we move on to the next part. And let's see if we can figure out what the coefficient of static friction would be between the coin and the turntable if the coin slides off the turntable when more than 12 centimeters from the center. All right, so here's a picture of a back view of the coin sitting on the turntable. I'm looking from behind the coin. Its tangential velocity is straight ahead on the slide. Okay, so straight ahead into your computer screen, and you're looking at the back of it. What forces are acting on this coin at this point? Well, we know that there's a gravitational force pointing downward and a normal force pointing upward. Those must cancel out because this coin is not accelerating vertically. Okay, but it is accelerating toward the center of the circle. And what's causing that centripetal acceleration, that centripetal force? Well, that centripetal force is a frictional force pulling toward the center of the circle. And that's going to be useful for me because I have these equations for centripetal force, and I have equations for friction forces, now I can equate those two together as I solve this problem. I also know that I still have a mass of 0.0017 kilograms. I'm going to carry that along from the previous question because it's the same coin as it was before. Let's see if I can solve for this. I'm going to carry along my period. My radius is, instead of being 0.052, now I'm at 0.12 because it's 12 centimeters. And again, because I'm using force potentially in here, because I'm using friction force, and the coefficient of friction is a ratio between two forces. So because of that, I have to have everything in kilograms, meters, and seconds. Here's my equation for the centripetal force using the period. 4 pi squared r over t squared gives us the centripetal acceleration. Then I need to multiply that by mass. But my centripetal force is a friction force. And I have an equation for friction force, the coefficient of friction times the normal force. And then if I look at this, I see that the normal force is the opposite of gravity because they're canceling each other out here. And I know that gravity is mg. And I'm just going to say that the normal force is the positive value of mg. We would say that gravity would be negative mg because it's pointing downward. So now I know a normal force that I can plug in. I'm going to plug that into my coefficient of friction equation. So it'd be the coefficient of static friction times mg is the friction force, okay? And that friction force is equal to the centripetal force, which is 4 pi squared mr over t squared. So now I should have everything I need to solve this, but look what happens to the mass. The mass is actually going to cancel. So it doesn't even matter that the mass is 0.0017 kilograms. This would apply to any coin of any mass that I put on the turntable. When a variable cancels out of an equation like this, it means that that variable actually has no effect on the phenomenon that I'm looking at. Okay, so if I simplify and get rid of those masses from the equation, this is what my simplified expression looks like. I'm actually going to divide both sides by g, that 9.8 right away, so I can get the coefficient of friction on a side by itself. Plug in all of the values that I know, because I know the radius, I know g, and I know the period. And then when I actually go through the math, I find that the coefficient of static friction must be 0.40 if the coin starts to slide off past 12 centimeters. Okay, so this was an interesting problem related to centripetal motion, uniform circular motion, but it's not universal gravitation like the title of this lesson says. And the reason we started with this problem is just to reinforce, first of all, our solution strategy for centripetal motion problems. Notice that I figured out what the centripetal force was, what the agent of the force was. In this case, it was friction. And then I set my friction equation equal to my centripetal force equation, the one that applied for this type of problem. Then I simplified, plugged in the values that I knew, and I solved for my unknown. That's a very typical solution strategy for these types of uniform circular motion problems. But now, how is this different from gravitation causing uniform circular motion? Well, keep in mind, friction force very often is a force that acts in the line of motion, not perpendicular to the line of motion. For a force to be centripetal, it has to be acting perpendicular to the line of motion. But a lot of times when we've worked with friction force so far, the friction force has opposed an object sliding in a forward direction or caused an object to roll in a forward direction, and it acted in the same line as motion. It wasn't causing an object to turn. Here's the thing about gravitation. Gravity is almost always a centripetal force. Now, we don't always have to treat it like a centripetal force, but it's almost always actually a centripetal force. And why is that? Because gravity pulls toward the center of mass of an object, and the objects that are capable of exerting a gravitational force tend to be huge, planet-sized, moon-sized, asteroid-sized objects. And those objects are so large that usually, if you have an object that has gravity acting on it, it's a distance away from the center of mass of the object exerting the gravitational force. Like right now, you have the Earth exerting a force on you. But the Earth is this big sphere, and it's exerting forces in all directions around the sphere.
So it's very easy to think of that force of gravity as a force being applied toward the center of a circle. And that's what makes it centripetal. It's being applied toward the center of a circle. Now, this has come up in physics before, but we really haven't dealt with it because we didn't have our understanding of centripetal force. But if you think about it, as we dealt with projectile motion problems, those two-dimensional kinematics problems where we threw a projectile into the air, did you notice that the projectile was actually changing the direction of its motion? It was turning. And the only thing that could cause it to turn is a force that's perpendicular to its direction of motion. And the way we envision those objects moving, we envisioned them moving at a constant speed in the x dimension, and the math worked out. So yes, they were moving at a constant speed in the x dimension, but in the y dimension, they were turning, moving parabolically. And why were they turning? Because they had a force being applied that was perpendicular to the x direction of motion. And that explains why objects turn in parabolic shapes as we experience them at the scale we're used to experiencing everyday objects. If you throw something horizontally through the air, it's going to turn toward the ground because the gravitational force is a centripetal force pointing toward the center of the earth, pointing perpendicular to the direction of the object's motion, and then changing its direction until it crashes into the ground. But here's the thing. You can make sense of the force of gravity of the earth being centripetal when you zoom way out and picture the earth as this giant sphere, and then just kind of picture where all of the gravitational lines are pointing. All gravitational lines will be pointing toward the center of the sphere. Okay, but you have to zoom way out to imagine it. Locally, when you consider like the room that you're in, or even the county that you're living in, the earth isn't curved enough for you to picture gravity as pointing toward the center of a circle. In that space where you're used to considering gravity acting, you're used to it acting more like something called a vector field instead of a centripetal force. Now, to demonstrate what a vector field is, I'm going to give you two examples, and one of them is going to be gravity. The other one's going to be more of a abstract example from physics, okay? Let's say that you have two charged plates, and I'm running electricity to these plates so that the bottom one is always charged positive and the top one is always charged negative. There's going to be forces between these two plates that are going to affect positive charges that I float in between here. So let's say I take some hydrogen and I ionize it, I remove its electrons so it's positively charged. What are those hydrogen atoms going to do if I insert them in between these two plates? Well, they're going to experience a force caused by the electricity. They're going to experience an even force because these plates are evenly charged everywhere on the plates. And notice that all of these field lines that I've drawn for these forces are evenly spaced. They're the same direction. And when I put these charges in here, it doesn't matter where I put them or even how big they are, they're all going to experience force in the same direction. Now, the size of the charge is going to affect the magnitude of the charge. Something that is twice as charged is going to experience twice the amount of force compared to something that has half the charge. And the way that we would calculate charge between plates like this in physics is we would use an equation like this. The force caused by the electric field is equal to the electric field strength. Usually that would be in something like newtons per coulomb times the amount of charge, which would be measured in coulombs. And I could further extend this by sharing you through what a typical electric field strength value might look like. So we might have something like this, an electric field strength of 2 newtons of force per microcoulomb. That mu isn't coefficient of friction. It is the metric prefix micro, which means 1 times 10 to the negative 6. So 1/1,000,000th of a coulomb of charge exerts 2 newtons of force. Now, this number may not make sense to you. We haven't studied coulombs of charge or electric fields in physics yet. But you can make sense of the fact that if we have 2 charged plates and a region between the plates that has this even spread of forces, then when we put a charge somewhere in between the 2 plates, it's going to experience a certain amount of force based on the electric field strength. And the greater the electric field strength, the more force there's going to be for every coulomb of charge. or the more charged a particle is, the more force it's going to experience. That's what that equation tells us. One more important point about fields, and this is probably the most important point about fields for our discussion. In that electric field, once I've established what the charge is of one of my particles, let's take that particle on the left that has 1 plus on it. Doesn't matter where I put it in the field, it's always going to experience the same amount of force per unit of charge. And because its charge is fixed, it's always going to experience the same force. So I can move it closer to the positive plate. That means that the negative plate is going to pull on it a little less, but the positive plate is going to push on it harder, causing it to experience the same amount of force regardless of where it is. Same with my particle that has 2 pluses. Its charge is fixed as having however much charge 2 pluses represents. So I can move that around in the field closer to the negative plate. Closer to the negative plate is going to pull at it more, but the positive plate's not going to push on it quite as hard. And the result is, regardless of where it is in the field, I can move it anywhere I want to in those lines. It's always going to experience the same amount of force in that field. Right now, how does this relate to gravity? Because we're not talking about electricity, we're talking about gravity. Well, here's the thing. This is a good comparison. It's easy to picture 2 plates across from one another like this and experience the lines between them. But locally, gravity acts the same way as the 2 plates act. And the reason for that is that the Earth is huge, except for locally, when we look at one small part of the Earth's surface, and it doesn't even have to be that small. Like this could be the size of a city, and it would still be small compared to the size of the Earth, right? Locally, when I look at a part of the Earth's surface, it looks as though the lines, which always point toward the center of the Earth, but locally, they basically are pointing downward in the same direction, parallel to one another. Because I'm looking at such a tight, small portion of the Earth's surface compared to looking at the Earth as a whole zoomed out. Okay, and when I have objects that are in that gravitational field experiencing those lines of force, they're going to experience those lines of force the same way as the electric charges between 2 plates did. I have this equation for the force of gravity in a gravitational field. We multiply the mass times the gravitational field strength. And we've already learned the gravitational field strength on Earth near the surface, 9.80 newtons per kilogram. So a larger mass is going to experience more gravitational force. A smaller mass is going to experience less gravitational force, but it doesn't matter where in the field the masses are moved to, that gravitational field strength is always going to be 9.8 newtons per kilogram. So the masses are going to experience the same force regardless of where I move them. Now that may seem a little counterintuitive, because shouldn't it be that when I move a mass far enough away from the Earth's surface, Earth isn't going to pull on it as hard? So I should experience less and less and less gravitational field strength the further I go away? Well, it's true that that actually does happen. It only happens negligibly. Here is a picture of the Earth, and we're zoomed way, way out from the Earth. The Earth is actually huge, right? So if I picture the gravitational field lines across the entire Earth, they would look something like this. Notice that they all point toward the center of the circle. Can you make sense from this picture of gravity as a centripetal force always pointing toward the center of mass of the Earth? And because they always point toward the center of mass of the Earth, and the Earth is huge, they're always pointing toward the center of a circle. But we're only looking at, when I'm looking locally, a very, very, very small region of the Earth. So this circle that I've drawn behind the Earth would be like the region of the Earth where we might want to consider the effects of gravity on an object for the purposes of our physics problems. Notice that it's only a very, very thin skin on the Earth, and I've probably overestimated it with the thickness of the circle I've placed around the Earth here. But not only is that area really thin, anytime I look at a region of the Earth's surface, I'm only looking at a very, very, very small region of the Earth's surface, like the distance between those two lines there. And again, I've overestimated the distance that we would be looking at for a normal frame of reference for a typical physics problem, like a car traveling down the freeway. It would be those lines would be much, much closer together. I'm just showing you this for effect so you can picture we're only looking at a very, very, very small region of the Earth. And because of that, it's almost as if we're looking into a gravitational field where all of the lines of force are essentially parallel to each other and pointing in the same direction. It's only because of the massive scale of the Earth that that's true, and those forces aren't like diagonally bent so they all point toward the center of the Earth. I can use math similarly to how we've been using math with centripetal forces to show you why it is that as you move further and further from the center of the Earth, the gravitational field strength doesn't get any significantly less than 9.8 newtons per kilogram. Okay, so let's just consider that the Earth is a giant circular object with radius r. And it's over that radius r that the Earth is actually exerting its gravitational force on somebody standing on the surface of the Earth, or an object that's sitting on the surface of the Earth, right? That force is always going to be exerted over the distance between that object and the center of mass of the Earth. We've used this equation many times. The force on that object is going to be mass times the gravitational field strength. This is our typical equation we've used to calculate force. But there is another equation that's used to calculate force, to calculate the gravitational force. And that's this one. It's been studied over time that gravity actually is a result. The force applied by gravity is a result of not just the mass of the object being pulled on, but the mass of the object doing the pulling. Okay, so both masses of both objects matter. And if you double the mass of one of the objects, it doubles the force of gravity. If you quadruple the mass, it quadruples the force of gravity. So we know that these have a direct relationship to each other, the mass of object 1, the mass of object 2, and we multiply those two masses together to affect the force of gravity. However, the farther apart those masses are, the less force of gravity between them there is. So that's why I have m1 times m2 divided by the radius, or really in this case, the radius just means the distance between the two objects, r. And it's not just divided by the distance proportionally, it's divided by the distance squared. Because as you move two objects further and further apart, the force between them actually decreases by an inverse square. And it's been studied again and again and again to determine that this is correct. Now, part of the way you could explain that square is as you move two objects apart, if I were to draw those force field lines, you would see that on the sphere, those force field lines spread out more and more and more the farther you get. They spread out over more and more area, which makes sense that I would have to divide by a square. But I can't get force in newtons just by multiplying the masses together and dividing by the distance between the two objects squared. I'll get a value that's related to the force, but it's not the force measured in newtons. What do I have to do to get the force into newtons? I have to multiply by a constant that will adjust all of the numbers to report what the number is in newtons. And that's what that capital G is. In physics, a variable like G is casually referred to as a fudge factor. It's just a number that we have to insert into an equation so that when we multiply the rest of the equation, which we know works, like we know that the force of gravity is related to the product of the masses divided by the distance between the two objects squared. That's been tested and tested and tested again and again. But it doesn't give us a value in newtons, and we need to multiply by another value to return our value in newtons. And that's what G does. It's not a nice clean constant like pi or the number 4, which we know exactly what those numbers mean and where they came from. We don't know why G is 6.67 times 10 to the negative 11th meters cubed per kilogram second squared. We just know that it has to be that to make the math work out correctly. We're going to use these two equations together to figure out what the value of the gravitational field strength is at the Earth's surface and at various heights above the Earth's surface. And to do that, we're actually going to need to know some more values to plug into this equation. Like we need to know the mass of the Earth. Well, it's been measured over many different trials. The mass of the Earth is about 5.97 times 10 to the 24th kilograms. We also need to know the radius of the Earth. So the distance from the center of mass of the Earth to like an object sitting on the surface of the Earth at sea level would be 6.371 times 10 to the 6 meters. That's 6.371 million meters. All right, so the Earth is huge. It just goes to reinforce. So same with the mass of the Earth. Look at the number of kilograms times 10 to the 24th is an immense mass for an object. That's why the Earth is able to exert gravity. And then lastly, we will need that constant g, 6.67 times 10 to the negative 11th meters cubed per kilogram second squared. That's the number. When we multiply by that, the unit label cancels out all of the unwanted values in our units and leaves us with newtons. Also, when we multiply by 6.67 times 10 to the negative 11th, it drops down the value that we would have if we just straight up multiplied the mass of a person times the mass of the Earth divided by the distance between that person and the center of the Earth. It drops it down to the actual force in newtons. Okay, let's go ahead and do our calculations here. I'm going to combine our two equations for Fg, the force of gravity. Notice that I have an m1 on both sides of this equation. That's the mass of the object that's experiencing the force of gravity from the Earth. On the right-hand side of the equation, I had to multiply both masses together, and I just designated them. One of them was the mass of the Earth. But on the left-hand side, the object that's experiencing the gravitational field has to be the object that is a distance away from the center of the Earth. So that's why I labeled both of those m sub 1, and that is going to cancel because it's on both sides of the equation. So what am I left with? G equals the gravitational constant times the mass of the Earth and divided by the radius of the Earth squared. This is the gravitational field strength that an object at the Earth's surface is going to experience. And when I punch in all those numbers to a calculator to figure this out, I find that the gravitational field strength is around 9.81 meters per second squared, or kilograms per newton, if that's the preferred label that we choose to use. And it turns out that that matches exactly what we find experimentally. I can also note that in Denver, Colorado, the Earth has a greater radius because you're a mile above sea level. The radius of the Earth is 6.373 times 10 to the 6. Now notice that that's really not that much different than the radius was at sea level. And the reason for that is because Earth is huge. And the area of the Earth that we wander around in, even when we go down into the deepest mine or fly in an airplane to the typical height that an airplane flies at about 20,000 feet, even if we climb to the top of Mount Everest, we're not really moving a significantly different amount from the radius of the Earth. You're moving around somewhat, but it's not enough to make this equation work out significantly differently. The value of G, the gravitational field strength of the Earth, is 9.80 in Denver, Colorado. And even at the top of Mount Everest, where it's typical height that airplanes would fly as well, we have the radius of the Earth being 6.380 times 10 to the 6. We get a G value of about 9.79 meters per second squared. Those variations are so small that you and I, with typical physics instruments, wouldn't be able to measure that difference. Now that's an interesting discussion of the universal gravitation equation and some practical applications of it, but we haven't brought in uniform circular motion yet. So let's consider how universal gravitation is related to uniform circular motion. And what happens is, when celestial objects, we zoom way out to look at things like planets and moons and stars, we find that celestial objects tend to move in approximately uniform circular paths at large scales. And when I say approximately, I mean we can approximate them as being uniformly circular, even though most of them are affected by other forces other than just the gravitation from like the central star or the central planet or whatever the central large object is. And as a result, they don't move in perfect circles. There's a little bit of oscillation, and most celestial objects actually move in ellipses. The farther out you go from the sun in the solar system, the more likely that the objects orbiting around the sun are to move in more elliptical paths than circular paths. However, we can estimate that the objects in the solar system at that scale are moving in approximately circular paths. Just note that estimate breaks down the farther away you get from the central object. We can say that the centripetal force for a celestial object is gravity. Gravity is what's causing that centripetal force for objects to orbit one another. Those two objects are pulling on one another according to their masses. The more massive object we picture to be at the center of the circle, the less massive object on the outside of the circle, moving around the circle. And we can use that equation along with our centripetal force equations to do some calculations. So think about this problem. Mars has two moons, Phobos and Deimos. The names of Mars's moons mean fear and terror, just so you know. So I know Elon Musk is trying to get people to move to Mars, but they're going to have to do some PR on the names of Mars's moons if they're going to get me to move there. Astronomers have measured the period of Phobos to be 0.32 Earth days, and the distance from the center of Mars to the center of Phobos is 9.375 times 10 to the third kilometers. Or a lot of times you'll see these written in scientific notation, but we can simplify that and just write 9,375 kilometers. From these values, find the mass of Mars. Now, a lot of times with these universal gravitation problems, we're going to be asked to find something that doesn't seem like it should be findable from the values that we have. But when we start putting equations together, you'll be able to piece together a solution how we will find that value. First of all, let's just look at a diagram of our problem. Here's Mars, here's Phobos. Phobos is orbiting Mars at a certain radius. We can represent it like this. We also know that this is a centripetal motion problem. So we're going to have a tangential velocity. Notice that this is a tangent to the circle. And a centripetal force that's pulling Phobos toward Mars, but it's pulling perpendicular to the path of motion, and therefore Phobos is going to be moving in a circle around Mars. Our equation for centripetal force and period is 4 pi squared times the mass times the radius divided by t squared. I'm going to put a little subscript 1 in there, and I'm just going to note right away that 1 is going to denote the object that's moving in a circle, not the central object, the object that's moving in a circle. And then I also have this universal gravitation equation, G times M1 times M2. So I'm multiplying together both masses. One of them is going to be the mass of Mars, that's capital M. One of them is going to be the mass of the smaller object, divided by the radius between the two objects squared. And then because the only net force acting on my moon here on Phobos is gravitation, that perpendicular force. I don't have any other net forces mentioned in here. What other net force could there possibly be that would be external to Phobos? There's nothing in space that's going to apply a contact force other than other gravitational forces, but nothing's close enough to Phobos compared to how close Mars is to significantly impact its motion. So the net force is going to be the gravitation force, and I can see that that gravitation force is always going to point toward the center of a circle, so that's always going to be a centripetal force. So now I know that Fg is equal to Fc, and those two equations that I have can be equated to one another, and that's what I'm going to do here. Anything that's found on both sides of the equation can be canceled out. So the mass of Phobos is not necessary to know. I can cancel that out of the equation. And if I solve for the mass of Mars, which is what I'm looking for, let's just take a look at the other side of this and see if I know everything else or if everything else is a universal constant. So I have 4 pi squared r cubed. Do I know the distance between Phobos and Mars? Yep, that was one of the things that I was given. Divided by the universal gravitation constant, that's a constant, times the period of Phobos squared. And I know the period is 0.32 Earth days. Now here's the thing. Within the universal gravitation constant, there are kilograms, meters, and seconds. So I need all of my variables here to be in kilograms, meters, or seconds. That means that the mass I'm calculating is going to be in kilograms, but I need to make sure that my radius is in meters and my period is in seconds for this to work with the g value that I'm using. 6.67 times 10 to the negative 11th is in meters cubed, meters, so I need meters, meters cubed divided by kilograms, seconds squared. So I need seconds, okay? Anytime you use a constant value or anytime you're calculating in a unit that has other units in it, I need to make sure everything's in the right units. And in this case, it has to be kilograms, meters, and seconds. So I need to change the period of phobos from days to seconds. And how am I going to do that? Well, I'm just going to use a series of conversion factors. There's 24 hours in an Earth day, 24 hours per day, so I can cancel out days and I'm left with hours. Then there's 60 minutes in an hour. Well, that cancels out hours. And then 60 seconds in 1 minute to cancel out minutes. And I'm left with 28,000 seconds in 0.32 days. Now I have a t value to plug in. I'm also going to need to adjust my r value, but I could just do that in my head because it's already in scientific notation. I just have to add 3 zeros. So I'm going to change it from 10 to the third to 10 to the sixth to get it into meters. And I'm going to do the math here. Multiply 4 pi squared times the radius cubed. Need to make sure to cube that radius. Divided by the universal gravitation constant times the period squared. Notice that I'm using the actual value for the period, 27,648 seconds. That was my actual calculated value. Up above, I wrote 28,000 seconds because that was in the right number of sig figs as my initial value was 0.32. So I'm going to go ahead and do these calculations. I find that the mass of Mars is 6.38 times 10 to the third kilograms. And if you check a table of values related to Mars, you can verify on the internet that the mass of Mars is around 6.38 times 10 to the 23rd kilograms. All right, so I was able to use the orbiting period of one of Mars's satellites along with its distance from Mars to figure out the mass of Mars. And that's a really cool indirect way that I can study planets. By studying their satellites, I can figure out characteristics of a planet just by looking at things like the moons that are orbiting it. Okay, let's see if I can answer a follow-up question. The period of Deimos, another moon of Mars, is 1.26 Earth days. How far is Deimos from Mars's center? Now watch the solution strategy for a question like this because this is typical of how some solutions work for centripetal problems that involve a certain kind of force, especially with universal gravitation, where I have a whole bunch of values on both sides of the equation that relate to one another. All right, so here I'm just going to represent Phobos again, and Deimos is going to be further out because it has a longer period, so it must be further away. There's Deimos, okay? Phobos and Deimos orbiting around Mars. Knowing what I do about this system, can I figure out the radius of Deimos? Well, let's get our equations back out here. So here's my centripetal force equation for period. And once again, for either of these two objects, as long as I analyze them one at a time, the only force that's acting on them is the force of gravity from Mars. Okay, so I'm just analyzing the force of gravity from Mars on each of these two objects because Mars is so large compared to the mass of either Phobos or Deimos that it's the only thing that's going to have a significant pull that's worth measuring here. And that's going to be a centripetal force out in space. So once again, I can bring in my universal gravitation equation and set these two expressions equal to one another. And once again, the mass of the satellite of the smaller object doesn't matter. It's going to cancel out on both sides. Now let's just write this equation out a specific way. I'm going to multiply both sides by r squared to get r squared off the right side and on the left. I'm going to divide both sides by 4 pi squared to get 4 pi squared over on the right. And just take a look at this expression. On the left, I have the radius and the period, which you know are variable. Okay, we don't know what the radius of of Deimos is. We're looking for that value. And we know the orbital period is different between Phobos and Deimos. So that's going to be a different value for each moon. Same with the radius. The radius is going to be different for each one. So we would consider that R and T would be variables. What about the other side of this equation for this system? G is universally constant. The mass of Mars, that's big M, is constant for this system. Okay, so I'm just thinking about satellites of Mars. The mass of Mars is going to be the same. And then 4 and pi are both obviously constant. So what's on the right-hand side of this equation is always constant for things that orbit Mars. What's on the left-hand side is going to change depending on the object specifically that's orbiting Mars. Specifically, how far away it is going to affect its speed and its orbital period, right? So let's take a look at what this would look like if we were calculating this for Phobos. I know all of these values for Phobos. And let's take a look at what this would look like if I was calculating it for Deimos, which is what I'm looking for. Notice that on the right-hand side of this equation, I have all constants. On the left-hand side of this equation, I have variables. What if I just set these equal to each other, because they're both equal to the same thing? So the ratio of the radius of Phobos from Mars cubed to the period of Phobos around Mars squared is equal to the radius of Deimos from Mars cubed, or the distance between Deimos and Mars cubed, divided by the period of Deimos around Mars squared. All I did was I set these two equations equal to each other, and I arrived at this relationship, and this relationship works. This is actually Kepler's third law of planetary motion, studied by a scientist from the 1600s who found out that this relationship does in fact hold true for planets orbiting the sun and for moons orbiting planets. The key is that the two objects that you're looking at and comparing their ratios here, they have to be orbiting around the same central body. Or in other words, up above, the mass of the central object has to be the same for both equations for you to equate them to one another. Another really cool thing about this equation, there's no G value, universal gravitation value in it. There's no force values in it because all of that got canceled out when I set equations equal to one another. So I don't have to use any specific units for radius and period. I just have to be consistent. I can plug in days for the period, and I can plug in kilometers for my radii, and it's still going to work out correctly. So let's go ahead and do that. Here I can calculate the radius of Deimos. So the distance between Deimos and the center of mass of Mars is going to be the cube root of the distance between Phobos and the center of mass of Mars cubed times the period of Deimos squared divided by the period of Phobos squared. I'm going to plug all of these values into my equation, very carefully remembering that I'm going to need to take the cube root of this whole thing, not just the square root. And when I calculate this, I find that the distance between Deimos and the center of mass of Mars is about 23,000 kilometers, which according to the internet, when I just look up that value, because that's been calculated, it's known, it's out there, is the correct value. Now remember, the reason that worked is because I didn't have any other variables in my equation that had unit labels that required me to have kilograms, meters, and seconds. If there was anything in my equation that had newtons as a unit label, I would have had to convert everything. Finishing up, there's just one more point that I would like to make. There are some centripetal forces that can be applied that can make circular motion happen with any mass of an object moving in a circle, any radial distance from the center of the circle to where the object is, and any tangential velocity. We've seen examples of centripetal forces that are very flexible and can have any mass, radius, and velocity. However, anytime the net force that is a centripetal force is dependent on the mass of the object that's moving in circles, you're going to find that that mass is going to cancel out. And we can't have any value of m, any value of r, any value of v, and any period. Instead, we're going to have a specific m, r, v, or period. And gravitation is one of those values because universal gravitation depends on the mass of the orbiting object. When gravitation is a centripetal force, a net force causing centripetal uniform circular motion, that motion is going to be independent of the mass of the object that's orbiting. Here again is our equation that we found when we equated universal gravitation to our centripetal force equation. Everything on the right of this equation is constant. And what that means is that there's going to be one distance from the center of the circle associated with each time period that it takes to make one complete revolution. Or another way we can think about this is there's one velocity, tangential velocity for an orbiting satellite associated with each distance from the center of the circle. Now, that's difficult to make sense of abstractly like this. So consider this. Let's say that we launch a satellite from the Earth's surface that's moving at a certain orbital velocity around the Earth. It's going to settle into an orbit based on the velocity that it has. And then let's say that we speed up the satellite. It has boosters on it, so we use some fuel to speed it up a bit. That satellite is going to settle into a new higher orbit associated with its new tangential velocity. There's just one orbit associated with every tangential velocity, and that's because there's just one velocity associated with every radius, the same as there's one period associated with every radius. That's also true for our centripetal motion problem that involved the force of friction. For a static coefficient of friction, there's just one radius where the object is going to max out that force of static friction. Now, friction, remember, works over a range of different values, so that if the object is moving slowly enough in a circle, like more toward the center, it's not going to overcome the force of friction. Friction is going to rise to the amount needed to keep the object in place. And as we move it further and further out, there's going to be one position where it's far enough away from the center of the circle that it just barely maxes out the force of static friction. And then if we move it a little bit beyond that, it's going to go flying off. When I look at the equation, I find that the mass of the object doesn't matter. What matters is the radius and the period. And there's one period associated with each radius that will max out that static friction force. So when I calculate this according to whatever my coefficient of static friction is, I'm going to find that one radius that's the maximum amount I can put the object away from the center of the turntable before it slides off. But there are some cases where it doesn't matter. Tension doesn't have any special equation that I use to calculate it, and tension can take on any range of values. So I can swing a stopper tied to a string around my head at various different speeds. So I could have different tangential velocities and different periods, and it's completely manipulatable. So I could speed it up or slow it down in the same radius. It could take on multiple values for the tangential velocity with the same radius by just varying the amount of tension force in the string. And it's possible for me to switch that. If I look at this equation, I see that on the right-hand side I have radius and I have the period. On the left side, I have tension force, but tension force is variable too. Because everything is variable, I don't have any of these variables that cancel out of this equation to fix my radius according to its period. Because everything is variable, in this system, I'm able to take on a range of different values for the tangential velocity or the period just based on how much tension force I apply. And I can apply as much or as little tension force as I'm able to this system to make it move in a variety of different ways. So hopefully it helps you understand a little bit more about universal gravitation, a very important concept in physics to understand. You should also understand a little bit more about plugging in our centripetal force equation to other equations related to centripetal forces, specifically specific agents that cause specific kinds of forces, to solve for unknowns in centripetal force problems.